Okay, so we're looking at Calc 1, Section 5.1. Once again, talking approximating areas under curves. We talked about Riemann sum. We talked about displacement. We're going to look at problem number 10. Okay, so problem number 10 talks about approximating displacement. We talk about the velocity in feet per second of an object is moving along a line in this curve. So velocity equals the square root of 10t. Once again, we want to know on the interval from 1 less than or equal to t less than or equal to 7. So in the book, they kind of graph this out for us. I'm going to kind of just relate our basic curve in here. So we talk about 2, 4, 6, 8, and then they go 1, 2, 4, 5, 6, 7. So we have 1, 2, 3, 4, 5, 6, 7 right here. And they plot this first point roughly here, second point roughly right up here. So we're seeing we have some curve, kind of like this is how this graph is looking. Okay, once again, if we were to graph this, it'd be something along this line. Once again, not perfect, just kind of do an estimate of what we're talking about. They tell us basically to break this problem into a couple different parts. First part, they say, okay, let's consider doing this problem with n, so part A, n equals 3 intervals, okay? And then they describe how we subdivide. So when we think about this, if we think about what's happening here, our delta x is going to equal 7 minus 1 over 3. So if I take 7 minus 1 is 6 over 3, talks about 2. So that means what we're doing is we're taking every, starting at 1, going 2 over, and then going 2 over. We see that we broke this into 3 equal width categories, is what this is relating towards. Now what we want to do is we want to find our midpoint on here, and then we're going to find all our values. So if I look at my midpoint on here, my midpoint is going to come up to this point here, this point here, this point here, and we're looking at basically drawing a horizontal line, and we're finding our values below. Okay, so we have our values that we're looking at here. And we want to find the area because once again it tells us to approximate the displacement. The displacement is going to be the total area under this curve from what these values are relating towards. So what we need to do is we need to basically take our function formula and we're going to plug 2 in, and then we're going to multiply by our delta x, which is 2, plus then we're going to take our velocity formula, our function formula, we're going to plug in then 4, because once again in between 3 and 5, 4 is that midpoint value right here, and we're going to multiply that by 2, plus then we're going to take our velocity formula, we plug 6 in, and then multiply by 2. So if we're seeing kind of what's going on here in summation format, we're basically taking the summation of our different velocities, so our velocity of 2, plus our velocity of 4, plus our velocity of 6. Now granted, this is not proper notation. We're taking the summation of these, and then this is all multiplied by 2, because once again we can factor a 2 out of everything. So we can figure out what all these heights are, add all those heights together, then multiply by 2, and that's how we kind of simplify those formulas down within here. Either way we do this, we got to figure out, we got to find what this is. So we're going to take the square root of 20 times 2, because once again we're going to plug 2 into here, so 10 times 2 is 20, plus then the square root of 40 times 2, plus then the square root of 60 times 2. And then once again, because we're approximating, we're not going to an exact answer, so we're not going to leave this in radical form on here. We see that we get 37.085 for our approximate displacement. Now once again, this would be in feet, so we'd see that overall we would see that this object on this curve would have traveled 37.085 feet in this. Now, once again, it's approximation because in part B now, so we change colors here. In part B says, okay, using the same thing, now let's use n equals 6. Okay, so if n equals 6 now, what we would do is we still would take our delta x, we would take 7 minus 1, but now we're going to divide by 6, so we see 1. So we're seeing now that every interval we have is happening every 1 unit. Okay, so now we're happening every 1, so we have 6 different rectangles that we're relating in here. And then once again it tells us to take the midpoint, so we're going to take the midpoint, which is going to be in the middle of each of these. So we see that we have this now. Where now we're a little bit more defined closer to our line. Okay, so if we think about this, we're going to have to do the same thing. We're going to have to take our velocity function, and now we're going to plug in the midpoint of 1 and 2 would be 1.5. Once again, then times 1. Sorry, we have a width of 1 here. I was relating back to our other problem, but now we got a width of 1 instead of 2. And then plus our velocity of, now we're going to go 2.5 times 1. Plus our velocity function 3.5 times 1. Plus our velocity function 4.5 times 1. Plus our velocity function of 5.5 times 1. Plus our velocity function of 6.5 times 1. So once again, all our midpoint, all our heights, we're going to have to figure out what are the values that's on here actually giving us that height that would be going up. So we're basically going to be taking the square root of 15 plus the square root of 25 plus the square root of 35 plus the square root of 45 plus the square root of 55 plus the square root of 65. Kind of went through here basically I'm taking 10 times each of these values and then taking the square root of that. And then multiplying by 1, so I don't need to write the whole multiplication of 1 in there because it is that multiplicative identity property. So if we consider that, then typing this in, once again it's an approximation, we get 36.976, once again, feet. So we start seeing that we start getting a little bit more defined down in these intervals as we start collecting our information better on here. And that's kind of what this problem is relating to. So we're just going to continue on and work some more problems. So let's go to number 12. Okay. On number 12 here, they give us information when they talk about V equals e to the t power meters per second. And they tell us we want to know our displacement as time elapsed from 0 seconds to 3 seconds. And we're going to break this into 3 intervals. Okay. So we need to know our delta x. Delta x, we're going to take 3 minus 0 and then divide by 3. So once again, this minus this divided by that tells us every 1 is what we're having. So now if we were to consider what's happening here, you don't always have to graph these, but do realize this is e to the t power. So at 0 we're at 1, and then we'll come 1 second over, 2 seconds over, 3 seconds over. Once again, we're going every 1 second from 0 to 3. So notice out to 3 seconds we have our happening here. And this is an exponential curve, so it has something coming up towards this. And then we're breaking it into all our parts on here. Now, depending upon how we're looking at this, what we want to do on this one, it tells us to use the left endpoint. Okay, so I'm just going to go like this and put a left hand on here. Generally, this is my abbreviation. Left hand, R would be right hand, and then M would be our midpoint, or just a mid on there for the consideration of what's happening. If we're using our left hand, that means our height is based off of the left side value of this interval. So we're using our values right here for our heights. That's talking about the rectangles that would be underneath this. So considering what is happening here, we are taking e to the 0 power times 1 plus e to the first power times 1. Plus then we would have our e squared times 1. Once again, we're looking at the height. This is our e to the t curve, so I'm going to plug 0 in, 1 in, 2 in. If I did the right side, I'd be plugging 1, 2, and 3 in, but then our overall rectangles would be above our curve. So that's kind of what we're looking at on here. So if we were to approximate this, this would be 1 plus e squared overall, approximately 11.1. Once again, meters on here because we're talking about the displacement or that distance that this would be traveling. Now, once again, this would be a low hand value. If you notice, all our areas are completely under. We're missing some of those areas in there. So that's where things kind of start changing a little bit depending upon what we're referencing and how we start looking at problems. Let's do the right hand value on here. It doesn't ask us to do it on this problem overall, but let's do a right hand one. So if we do a right hand, what we would look at here is we would look at now that right side. Okay, so let me just change colors here and let's underline it in blue. So if we go right hand, we're looking at these. So we're looking at this now as we would be above this, and we'd have this right here. So now we would have e to the first times 1 plus e squared times 1 plus e cubed times 1. And then this would approximately be, once again, I have my calculator out on this one. I don't have this one fully worked out. We would have e to the first plus e squared plus e cubed, which would give us then approximately 30.2 meters. Okay, and then if we wanted to do a midpoint one, let me find a different color here. If we want to do a midpoint one, once again the midpoint would be right in the middle here. Okay, so if we see this midpoint one kind of breaks where this area and then this area kind of above and below in here. So if we want to do a midpoint one, we would look at e to the 1.5 times 1 plus e to the 2.5 times 1 plus e to the 3.5 times 1. So then if I just come back into my problem in here and change my values to add those 0.5s, we would see that this would then be approximately, oh, I did it the wrong way. Why didn't you catch me on that? You guys got to speak up out there. 3.5 put me out here. This is really 2.5, 1.5, and 0.5. So we see that we get 18.3 meters. Now, one of the main reasons why I caught myself on here, and one of the things we kind of start talking about, once again, depends upon the curve. If I see this curve is always in that upward fashion, when I do that left-hand side, my rectangles are always below the line. So that's a low when I have rectangles that are always above the line, like my right-hand side. So I knew my midpoint had to be somewhere in between these two, once again, because this is going up. But as we get curves where they go up and then down, and we start going back and forth, then we're not going to see this pattern as we continue to work through problems. So this is kind of the basics of what goes into Riemann sums. What we start looking at, let's look at another example. Let's jump over to number 32. Okay. On number 32, it tells us that given the function f of x equals x squared, interval 0 to 4 inclusive, and we talk about n equals 4. Here it tells us to perform the midpoint Riemann sum. Okay, so once again, to do the midpoint Riemann sum, we're looking at, we need to figure out what delta x would be. So delta x would be 4 minus 0 divided by 4, so that would be 1. So if we consider what's happening on this graph, once again, it's an x squared graph. We have a vertex at the origin, and then we would have this curve going out, kind of like this overall as that x squared function. What we'd be looking at right now is we'd be looking at from 0 to 4. So if I go 1, 2, 3, 4 right here, this is what we'd be looking at. We'd be looking at this section of the graph. And because we're doing the midpoint, we would value our heights to be in the center of this. Okay, so if I just quick grab a different color so you can see what's happening, we're valuing this right here. Where our rectangles below, the height is that midpoint value, so in the middle of each of these as we go through. So we see that we have 4 different rectangles. That's what that n equals 4 is on the interval here. Each has a width of 1. So now basically what we're going to do is we're going to be plugging in our values. So we're going to have 0.5 or 1/2. We're going to plug that into our function because that's going to give us our overall height right here, times our width of 1. Plus then we're going to go 1.5 squared times 1, plus 2.5 squared times 1, plus 3.5 squared times 1. Okay? Once again, thinking about everything that's going into this, we have the height here, the height here, the height here, the height here, so that's these overall heights of this. And then we're going to be adding all these together as what Riemann sum says. So this is having 1/4 plus 9/4 plus 25/4 plus 49/4. So we see that overall we have a sum of 21. Now once again, this is how the midpoint would be. If we did a left hand, we'd be looking at that left hand side, in which then on this left hand side we'd have an area of 0 in this first one because the value at 0 is 0. So it'd be pretty kind of starting to get misleading in that information, which is why the book had chosen one to look at in here. Now, kind of just walking through a couple other examples on here. I have my notes in my book here, so just kind of showing you. When they talk about summations, we talk about 1 to 45 here. So the summation from k equals 1 to 45 of k. Once again, k was a value in here, so we took 45 times 45. So this is just kind of working through some of those in here. Do notice that on like number F right here, from 1 to 20 of 3j minus 4. Remember that summations had our properties kind of like our derivatives had, where we could take that subtraction out as a constant in here. We could take that scale factor 3 times each one that we're substituting in. We could take the sum of what all this is and then multiply by 3. So it just kind of gives a way to break down that problem. So you can kind of see I just used the formulas right here for those summations and showed you how they go. This is a constant one. This is a j1 in here. The h1, when we have an n squared, plus 3 times the summation of n minus the summation of 1. Basically for every 0 to 40 we're putting in here, so 41 numbers. We're subtracting 1 off each and every time, so that's where that kind of that minus this comes in here as we start considering. So this is where we get our values then, kind of summing up things. What I really want to show you is over here on number 64. Okay, so number 64, I have it worked on the side for the 3 different Riemann sums. It tells us to approximate the area of the region bound by this graph. Okay, it tells us to use a left hand and right hand sum to obtain 2 different approximations. So what it is they told us 3 different ones, and we're interval from 0 to 6. So that means I have 6 minus 0 divided by 3 is every 2. So if you notice, I have my line drawn in here. So this is my intervals. The left-hand one says that now, on this first interval, we're going to have a height here of 1. and then we're talking underneath of 2. So that's where that 1 times 2 comes from. Now our left-hand height of this one is 6 times 2, and then right here we have 9 times 2. We add all that together, we see we have an area of 32. On the right-hand Riemann sum means we're going to take the height from the right side. So that means we have a height of 6, and we got this larger rectangle that's going in here. So we see where this first one had an area of only 2 units. Now we're seeing an area of 12 units being considered here. Plus then now we have a 9, plus then we have 11 then for this final height right here. One thing to be thinking about with the left hand and right hand sum, if you notice, 6 times 2 plus 9 times 2, 6 times 2 plus 9 times 2, it changes these outside ones, okay? So it either adds in the extra outside one or takes away that first one when we look at that left hand going to the right hand. The midpoint, on the other hand, is completely different. If we looked at the midpoint on here, we would have to go to 1, and the value of 1 would be 4. So that's where we have 4 times 2. Then to 3, we come up here, that'd be 7 times 2. And then at 5, we come up, and that's about 10 right here. So 10 times 2. If we notice, we have 32, 52, and then that midpoint would be 42. Is one better than another? In this case, I mean, that midpoint's probably a little more precise. But we see that it's directly in the middle of these two. Do not fall in that it's going to be directly in the middle of these. It all depends upon these curves and what values are in here. So do realize you're going to have to draw out, you're going to have to work through each one. At this point, we're not doing like 100 for n. Okay? That's where better calculus techniques come into play as we keep moving along in our sections.